Okay. So as we discussed, we can also use active solar systems. For example, okay, here we can see an active solar system. And it is divided into several components. So at the first stage, we need to collect the solar energy. Okay, for example, here we can use solar panels. These solar panels will be used to collect the solar energy. Now, we need, if you want now, to distribute this energy. Okay, in order to distribute this energy, we need a distribution system. So let's say, for example, you can use a heat exchanger, okay, circulating a fluid. This fluid will go through the solar panel. It will be heated. Okay, you want to circulate this water, so you have a piping system where water circulate. Now, to move your water inside the system, you need a pump, let's say. So this is where you need to supply electricity to circulate your water. So you circulate your water by a pump, by the mean of a pump, uh, and then it will go through the heat exchanger within the solar panel. It will be heated by the solar rays, so it will transport the solar energy collected at the level of panels. And now you will distribute this heat. In case you need it now, okay, and you can, of course, a part can be taken, let's say, to a reservoir that can be used to supply the water, domestic hot water needs, let's say shower, or use of water in the kitchen, etc. But what if you don't need it now? If you don't need it now, you need to store it. Okay. So we need until now a collector system, a distribution system, and now we need a storage system. Because if you don't need now the hot water, you need to preserve this heat. Okay. You can do it in several ways. For first, of course, you can have a certain reservoir of hot water. So when you need it, you can use it. But in case you need it after a long time, you might go to also storage medium. So let's say thermal storage medium, or let's say PCM material also here, that can store it for a long period of time and release it back whenever you need it. Okay, so you can see here, for example, what happened during the day. Let's say you don't need it now. Okay, so during the day, you have excess of solar energy. You don't need it. You don't need to use it now. So what happened is, when your fluid was circulating here, you have the option of taking it around the thermal storage medium. Okay, and as the fluid will circulate around the storage medium, thermal energy will be transferred from the fluid towards the thermal storage medium. And then during night, let's say, when you need, let's say, this heat, of course, you can not only use it for just domestic hot water needs, you can use it for heating also. You have the underfloor heating systems that are just relying on the idea of circulating hot water in pipes embedded below the floor level. So you can also use it as a way to heat your room, not only to use hot water. Okay, so here you can use at the same time hot water, plus you can replace ventilation systems. And this can be ensured by the distribution system that can give a part, let's say, to the reservoir, and will circulate another part around the bed in order to store this energy. And then whenever we need it, okay, let's say during night time, we can again circulate water towards the thermal storage place to take heat from it, and then we can give it back to the inner space. Okay, any question on this? Okay. So this is a small example of a strategic space planning whenever we want to design a building, a passive building. So let's say in the north facing, we can put the surface or the transition zone. because we'll not occupy it a lot, and we don't have sun in the a lot of sun during let's say the day. On the other hand, we can put in the north, we can create just a north facing buffer zone, while the primary occupied zone will be at the middle to reduce the heat losses through the envelope. And the south facing buffer zone will be subjected to passive solar heating because the south face is exposed to the large hour of suns during the winter season. Now, good interior layout will facilitate a lot the passive strategies, in particular thermal mass, lighting, and ventilation considerations. So we should ask ourselves, of course, what are the most frequently used rooms and what is the time of using these rooms in order to decide which strategies to implement, what are the lighting needs, and what is the external shading state. Now, if you want, whenever you do the design, you have recommendation for each part. So let's say for the kitchen. So the kitchen should ideally be located within the building in such a way as to avoid overheating. We should situate it on the eastern or northern elevation because it's not exposed a lot to the sun, or in a central space within the building. Concerning the living spaces, we should situate evening use rooms on the west elevation because it's exposed to the sun during evening. And we situate frequent use room on the south elevation. Okay, because the south is, in general, is exposed to for a large period of time to sun during winter. Concerning bedrooms, we situate bedrooms as comfort dictates. Windows should be kept to a minimum and should allow for passive ventilation. Now, concerning mechanical systems, bathrooms, kitchens, and laundry rooms should be placed above or adjacent to each other so that efficiencies of the plumbing system can be maximized. You know that we need active systems in all of these parts, bathrooms for the shower, and let's say, yani in bathrooms we have a lot of plumbing issues to put. For kitchens where we have cooking, we have a lot of activities also, and laundry rooms. All of these requires the placement of mechanical systems and of plumbing devices. That's why they should be close to each other to enhance the efficiency of these systems. You know that if you have large distances, this will reduce the efficiency of operation of the system and will increase the energy bits. We should minimize the building footprint by using short pipe runs, so hot cold water or sewage and ventilation ducts. We should place thermostats with due consideration to temperature variation within the buildings. Now, let us discuss, for example, how we can optimize, and this can show us how we can do optimal analysis whenever we want to do any passive strategy. Okay, let us say we want to design a glazing facade. Okay, and we want to determine what is the glazing ratio that should be used on this facade. This will always require optimization study. Why? Because you have some factors that will be enhanced by increasing the ratio of glazing. On the other hand, you have other factors that will be reduced. So for example, let us talk about lighting. Okay, of course, whenever you increase the glazing facade area, the energy consumption for lighting will be reduced a lot because you can use during the day just light from the sun. Okay, so in this way you can reduce a lot the lighting consumption, and this is one of the big advantages of increasing the glazing ratio. Okay, now, on the other hand, whenever you increase the glazing ratio, you will increase the ventilation needs because you will have more interaction between the inner and outer space. Okay. Of course, sometimes increasing the glazing ratio can allow sun to penetrate, let's say in winter, and this is desirable. But in overall, if we calculate over the whole year, the heating and cooling loads will increase if you increase the glazing ratio. Okay, and as you can see, the rate of increase is increasing as the ratio will increase. So let's say you can explore here, for example, for when you are lower than 40%, the increase is little bit at a smaller rate. But if you increase a lot the ratio, the glazing ratio facade, you will start to have high rate of increase in the energy consumption. So now, okay, what you can do is you can do the summation. So I will sum the lighting energy consumption, the cooling energy consumption, and the heating electricity consumption. And I will optimize then when I find the minimal consumption, this will give me the optimal glazing ratio. So when you sum all of these loads, okay, you can see that to reduce to the maximum the energy used per meter square of facade, for example, here nearly I need nearly a ratio of 37%. Okay, nearly. And I can play in a certain range if you want, because I can see that if I vary between, for example, a ratio of 25%, let's say, and 55%, I don't have really large variation in energy consumption. So on the economical level, if I do an economical study, I can say no, maybe it's better to it's enough to just put 25, because I can reduce in this way the initial investment while I can still obtain a very good performance in energy reduction. Okay, so from here, it's not enough just to do this study. I should do also the economical study in parallel, because I can have a range of acceptable values, and then the economical analysis will tell me maybe it's better to stick to this value because it allows to reduce considerably the energy consumption, while the initial investment will be lower with a smaller glazing ratio, let's say. Okay. So now here we have some recommendations, if you want, on the level of insulations resistance presented by the envelope in different countries. So of course, the recommendations will not be the same for different climates, because whenever you have a moderate climate, the difference in temperature between the inner and outer side will not be very large. So this will allow to go for, if you want, lighter envelopes and lower insulation. Okay, so here, for example, we are comparing the R values of walls, including installed insulation and other layers that should lie in the interval indicated in the table for, let's say, a small residential building of 140 meters square, one story, single family. And as you can see, also the specification of the building should be given, because each type of buildings will impose different restrictions. Okay, so as you can see here, as you go from mild to very harsh climate, you need to increase the resistance values. Okay, because for very extreme climates, you need to ensure a much better insulation, because the difference in temperature between the inner and outer side is really considerable. Now, another source of heat exchange between the interior of your building and the outdoor environment is the roof. And the roof also, we have a lot of strategies that can be used for roof insulation. So for three reasons, it is common practice to employ higher levels of insulation in the ceiling rather than the wall. First, it's cheaper to insulate the ceiling than the wall. Second, the temperature stratification causes larger heat loss rates per unit area of ceiling rather than per unit wall area. So mainly the roof is one of the main sources of heat losses. That's why it's important to insulate it appropriately. Solar gains on roofs during the summer can cause unwanted heating of the living space beyond that caused by high ambient air temperature. That's why it's very important to insulate the roof appropriately. Now, if you remember, we discussed also the infiltration. So we talked about the heat loss by infiltration, and we said that we can calculate it as the flux of heat is m dot Cp delta T. Okay, so this one can give us the rate of heat loss by infiltration. It's true that we don't want to have a high value of infiltration because we don't want to increase the losses, but we have to not go beyond below a certain minimum because infiltration is important to renew, let's say, air in your room. So many older buildings have infiltration rates as high as 1.5 air change per hour, which is really high. A reduction to 1 air change per hour may be achieved by employing a plastic vapor barrier, taking care to seal all joints and foam any cracks, which will generally further reduce the infiltration rate to zero point 0.5 air change per hour. هلا you have actually recommendations for minimal air change per hour. We should not go below this minimum. Okay, because if we go below this minimum, we'll have indoor air quality issues, and this can cause health problems. Okay, so we should avoid high infiltration rates, but of course we should allow a certain minimum air change per hour. So it is strongly recommended that the infiltration rate be limited to zero point 0.5 air change per hour. So whenever you do a design, this can be one of your numbers that you should respect for both new construction and retrofits whenever possible, since extremely low rates may be hazardous to occupant health due to accumulation of indoor pollutants. Further reductions in infiltration heat loss should be attempted only through the use of window heat recovery units. Extensive use of these units can yield effective infiltration rates as low as 0.187, and under certain circumstances, this can cause the additional expense involved may be justifiable. Okay, so it depends, as we mentioned. Always, we should do an economical analysis in parallel to see if we know that if we can reduce the infiltration rate, we can enhance the if you want the energy consumption will be reduced because will reduce the heating and cooling loads. Okay, so it's good to implement strategies to reduce infiltration. If we want to go below zero point 0.5, as we mentioned, we should install more windows because we can study, if you want, the opening and the operation of windows in a way to always have fresh air inside the room in order to avoid indoor air quality problems. Okay, uh, but if we reach a very low level of infiltration, this might be good on the energy bill level, but also you should pay attention that to in order to reduce it to such amount, maybe you will put a very high investment also. So you should verify economically that the investment you put to reach such low values will be justifiable. Okay, so that's why always we say whenever we suggest to implement any strategy, we should do the economical analysis in parallel to justify that we need to go to such low level. If you calculate that if we reduce to zero point 0.5 the air change per hour, I will be really fine with the energy reduction. Then no need to go to very, very small values because this might not be justifiable on the economical level. On the other hand, if you find that if I reduce more and I don't have a very high investment cost, I will be able to reduce more and more the energy bills, I can go for it. But of course, pay attention for the also indoor air quality requirement. So if I do this, I should make sure that I have windows, a number of windows that is enough, and that I am operating them in a good way to ensure always good indoor air quality in the space. Now, here is a simple example for a solar water heating system that can be used for space heating and domestic hot water. So, as we discussed, in such systems, we have mainly we need to collect the solar energy, we need to distribute it, and we need to store it. So, a very simple system consists of the following element. You have the collector, and you have a primary loop of circulation of a fluid through a pump. The pump will allow circulation. Sometimes you can rely on density difference for circulation. So, but the flow rate that will circulate will not be very large. So you can use it if you want for applications of small, where you don't have a lot of energy to deliver. Whenever you have large amount of energy to deliver, you need a pump because the pump will accelerate your fluid, and this will help into storing more energy. Okay, so the pump will circulate your water, your fluid. It can be any fluid of high capacity, so it can store, if it can store, it can absorb energy from the collector. So the fluid will move through the collector. It will gain energy, so the absorbed energy from the collector will be transferred to the fluid. Then this fluid will pass through a heat exchanger to release back this heat. Now it can release it to a storage medium, and then the storage medium will give it to the indoor space whenever needed. So you will have another loop of circulation. So this is called the primary loop, where you have the fluid circulating in order to collect, in order to take the collected energy and store it. And after this, you have a second loop that will pass through the storage medium in order to take the energy whenever needed. So here we can see several systems. Okay, we talked about now the active system. This is the active system where you have a pump, and you can see here that after you store uh, your energy, you can distribute it. So here, this is a second loop. Okay, you have, for example, a distribution system. In the distribution system, you can have several paths. So let's say one path for extra energy, you can store it, let's say, using thermal mass or using phase change material, etc. You can supply it directly, let's say, for domestic hot water needs. Okay, and another this is an active system because we have a pump. A passive system is the thermosiphon block. So it rely on thermosiphoning effects. What we mean by this is you rely on density differences to circulate your water. So as you can see here, you know that when you heat your water, as the temperature increase, okay, the density will decrease. And because of smaller density decrease, this will lead to motion due to buoyancy effect. Okay, because lower denser particles will tend to move down and lighter particles will tend to move up. So this will help into circulating water within this system. This system presents several limitations. You are limited to really small heights. So if you have buildings of several floors, it's not very effective, but at least for such house, it can work. Okay, and then you can avoid the use of pump and the electrical consumption of the pump. So it depends on the application. You can select active systems or passive systems. Now, as we mentioned, we can use uh, solar heating due to several purposes. You can use it not only to domestic hot water application, but also to space heating. So as we discussed, you can circulate your water, for example, underfloor. As you can see here in this figure, the heated water can be stored first, let's say, within a reservoir to be used for domestic hot water needs, as shower, as used in kitchen, etc. But also you can circulate it within ducts under the floor, and in this way you can ensure the heating of your space. Okay, so this is called the underfloor heating system. Now, we have several types of solar collectors, and depending on our application, we can select the most convenient one. Of course, let's say it depends on the amount of heating needed. So the first type, which is the simplest one and the cheaper one, is the unglazed collector. It has the advantage of being simple to install. It has a relatively 3 year to 6 year payback period, which is acceptable, and it can deliver up to 2 to 2.4 kilowatt hour per meter square per day. This is widely used for in pools. Okay, because let's say you want to heat water in pools to a temperature that is not very large. Okay, and this system can be very efficient for such application. Now, in case you need to reach larger temperatures, you can go to more sophisticated systems. For example, the glazed flat plate collector, it will consist of a glazing over that you put over the flat plate. This will help you into it will increase if you want the stored energy, because you know that glazing have good absorbance transmission properties, so it will transmit a high amount of energy to your collector, and then you can circulate a fluid within your collector, so it will act like a heat exchanger. You'll have an inlet and an outlet for fluids that can circulate, and then the heat that is transmitted through the glazing and trapped between the glazing and the heat exchanger will be transmitted to the fluids that can distributed for you to be used after. Uh, and another also more complicated system is the evacuated tube. It is, of course, the initial cost will be much larger, but you can store more energy and you can deliver a larger power. So the concept of evacuated tube is, if you want, it will consist of several concentric tubes, and this will allow to trap the solar energy in a much more efficient way, because you have outer glass and inner glass tube, and this will lead to a trap of the solar energy, and this will increase the proportions that can be transmitted to the fluid going through the evacuated tube. And of course, also, the concept of a circulating fluid is similar to the one for the glazed solar collector. So you have a fluid that is circulating within the tubes and will be heated as it passes through the system. So it depends on your application. What is the power needed? You will select the appropriate system, because, of course, as usual, the economical analysis will tell you if it's worth to go to this investment or not, because here you will have a much larger investment cost. So you study your system on the economical level. You can compare the three scenarios and see which one is, if your just application is to heat water for a swimming pool, the investment here will be too large. That's why you will not go for this option. So the economical analysis will tell you you can just go to the first option, which is the cheaper one, and it can allow you to satisfy your needs. So no need to go to additional cost and go to a complex system with larger initial investment. However, if you want, let's say, to supply a home with all its needs without relying on electricity, this can be a good strategy. So, for example, if we want to do some calculation, let's say, for the selection of appropriate solar active technologies in order to ensure domestic hot water needs. Okay, so what we should care for, we need several aspects to consider. Okay, first, of course, we have seasonal variations in the energy collected depending on location, collector efficiency, collector angle, and orientation, ranging from about, let's say, zero point 0.6 to 1 kilowatt hour per meter square per day. So we should know what is the capacity in winter, what is the capacity in summer. Sometimes maybe in winter we can have a backup system because the solar system might not be enough, while in winter the solar system can supply all needs, let's say, because for example, in winter uh, we can have up to in summer we can have up to 2.4 kilowatt hour per meter square per day. So once we know the capacity of our system, we should we should look at the needs. What is the number of occupants? What is the shower frequency? To in order to determine what is the heat needed that we should supply, and based on this, we can select the number of PV panels to use, etc. We'll discuss this if you want more in projects, because already some students suggested to use solar technologies to supply needs. So we can, whenever they expose their project, we'll discuss such issues, how to decide on the number of solar PV panels to have, what is the pump required, the sizing of the pump, if we need a backup system or not, etc. Here we can summarize, for example, the use of different types of collectors. So we already discussed three types of active technologies: unglazed collectors, glazed collectors, and evacuated tubes. So now, depending, of course, of the application, we do the selection. So as we discussed, for swimming pools, the amount of heating required is not very large. That's why unglazed collector might be the best choice, because it represents several advantages. It's economical, it's efficient at low temperature difference. Plus, it represents the advantage of having low cost. So when we do the economical analysis, it will represent the lowest investment. And therefore, when we calculate the benefits, we'll have much larger benefits when we go to this system, in case the application is just heat water for swimming pools. Now, the disadvantage is that uh, it's not opposing freezing. So let's say we cannot use it when we have temperature below freezing temperatures. Okay. The capital cost of such systems is between 150 to $350 per meter square, which is relatively a low investment cost, and it can produce annually between 210 and 250 kilowatt hour per meter square. Okay. Now, in case for glazed collectors, they are widely used for domestic hot water needs. They are also economical, and but at the same time, we need to provide protection from freezing. We should add, let's say, a fluid, circulating fluid that is against freezing. The capital cost, of course, compared to unglazed, is larger, but it can provide much larger energy consumption. So it is justified in case we have an application like domestic hot water needs, where we need to heat to a high temperature the water. Now, another type is the evacuated tube. And here we can provide larger energy delivery, but of course at a larger cost. So the advantage is that we can go to hotter water. So if we are in cold climates, okay, if we have, let's say, regions where we need, or applications, if you want, where you need very large temperature, let's say, you know that whenever you, for the shower, you need to heat first to a very large temperature before mixing it with cold water, because you need to kill some bacteria. Some bacteria can be killed at sufficiently high temperature. That's why you need to do some you need to reach relatively high temperatures. Okay. And in case you have a building with large energy consumption and you need a larger energy delivery, you can go to evacuated tubes. Now, the disadvantage also is that it's expensive. You have a high investment, but again, it can be justified by the higher energy delivered. So, in case you need such amount, then this project can be justifiable. So you can say, if I do an economical analysis, I can save a lot of, if my bill is 900 kilowatt hour per meter square, this is my electricity bill, then of course I can go for this system, because I will need all of the quantity it can deliver me. However, if my bill is just 700, so it's much, maybe if I do the economical analysis, it will be better to go for the second option, because I just need as backup system maybe just 100 kilowatt hour per meter square, but I will reduce a lot the initial investment. So again, what will tell me what to do is when I compare the different alternatives on the economical level. So my final decision will be affected a lot by the economical analysis. From here, the importance of energy economics. Another, just one final remark is the temperature range I'm working in. Okay. We talked already about unglazed type. We said that when delta T is relatively small, when I want just to heat to relatively, let's say, 24 degrees, for example, 25 degrees, this is the most efficient one. Why? Because the efficiency of if you want your collectors is very depending on temperature. And this graph is showing you the variation of efficiency with temperature. You can, if you look at the unglazed type, you have a drastic decrease in efficiency for large temperature. From here, you can see that you have a zone whenever we talk about, let's say, between 0 and 25, 22 nearly, okay, the efficiency of unglazed is very acceptable. It's above 80%, okay. That's why whenever we want to heat to relatively small temperature, we suggest the unglazed type. On the other hand, okay, for larger temperature applications where you need to reach larger temperature, we can see that the glazed, if you increase a lot the temperature, the efficiency will be reduced considerably. So let's say for just hot water, domestic hot water, it will work well because it can heat up to 80 degrees, and it's more than enough because in general we heat around 70, 72. Okay, so it's fine. The glazed and evacuated tube both are fine for domestic hot water application. What will decide which one to use, as we discussed, is the energy consumption, and if it's worth to invest in evacuated tube or not, because here we have a much larger initial investment. And in case we have other applications, and you have, for example, some industrial applications where you need to have very high temperatures of waters, then you can see that the evacuated tube is presents the best for performance because the reduction in energy efficiency with temperature is reduced a lot. So you can keep even for 140 degrees when you reach such large temperature, the efficiency is above 50%. Now, what is the design procedures that we should follow whenever we want to design solar active technologies? We should look at different parameters and follow different design steps. First, we should define the basic data about the building and climate. Second, we should determine if it's possible to obtain enough collector area. You know, sometimes you have the space limit. You have a very tall building, let's say, with high energy consumption, and you have a limit on the roof area. So you don't have a lot of space to put your collectors.